Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about the gravitational potential energy, and in particular, what to do in situations where it is no longer appropriate to treat the gravitational force as a constant. So when we think about the Newton's cannonball problem, we argued that in these kinds of problems where the object is traveling great distances and going to different elevations above the Earth, the law of gravity indicates that it is not okay, probably, to treat the gravitational force as a constant. So, what do we do if we want to deal with gravitational potential energy? And how do we know when we can approximate the gravitational potential energy in the old way, this MGH way, and when do we have to use this new form, which we're going to derive in this episode? So, let's dig in. So let me start by reminding you how things worked when the force was constant. So if we're in a situation where we can just say that the gravitational force acting on an object is equal to m times g, where g is this constant vector pointing in the negative y direction. How did we go from that statement to the statement of what the gravitational potential energy is? Well, the steps were we defined the change in the gravitational potential energy as minus the work done by gravity when you move from some initial configuration to some final configuration. And the way we calculated work in that case was we moved from some initial position to some final position, and the work was obtained by taking this integral of the force dotted into dr. And then we argued that in the case where the force was a constant, it was very easy to do the integral, and all that really ended up mattering was the change in elevation. So we ended up being able to write the change in gravitational potential energy when you changed elevation as mg times delta H, where delta H stands for the change in the elevation above the Earth's surface. So this is a true statement if the force of gravity can be treated as a constant. So let's treat the more general case. Let's imagine we've got some mass, we'll call it mass little m, and little m is located at some position, which we'll call r, relative to the center of the Earth. And the Earth in this story has a radius r sub e. And then we want to use Newton's law of gravity, to write down the force that the Earth exerts on our mass. So this gravitational force, according to Sir Isaac, is equal to minus big G times the mass of the Earth times the mass of our little mass divided by the distance from the center of the Earth to our mass squared. And then the direction is given by this r hat vector. So the minus sign out in front here ensures that this is an attractive force pulling on little m, exerting a force directed towards the center of the Earth. And, let's suppose this is the initial position of our mass, and it then moves to some other position in space, which has a location RF, like that. And we want to know what the change in the gravitational potential energy is in moving from this initial position R sub I via some path to this final position R sub F. And the rule for calculating the change in potential energy due to any conservative force, of course, gravity is an example of a conservative force, is to calculate minus the work done by that force in moving from this initial configuration to the final configuration. So the way we calculate the work in general is by doing an integral of F dot dr, like so. Now, as you probably realize, the result in general is only going to depend on changes in how far you are from the Earth. It doesn't matter if you're moving tangentially. All that matters is how far you are away from the center of the Earth when you start and how far away you are when you finish up. So it's a lot easier to think in terms of, instead of thinking of sort of in three dimensions, we can really think of this as a sort of one-dimensional problem where you're just changing the radial distance between from the center of the Earth to where the object is located. So we can rewrite this problem as a one-dimensional integral, an ordinary integral without vector signs, provided there's one little bit of trickiness. You can go crazy keeping track of the minus signs in this problem. We have to add a minus sign here because in this uh, in the vector version of this, f grav points in one direction and dr points in the other direction. So they're 180 degrees apart, and that introduces a minus sign. So we account for that by introducing this minus sign here, and then there's this minus sign here, which arose from the definition of how we calculate the change in potential energy. So the net effect of that is two minus signs exactly cancel, and we can just get rid of both of them, and that seems simpler. And now I'm going to plug in what the gravitational force law is. So we're the integral from our initial radial distance to the final radial distance, radial position or distance, g times the mass of the Earth times little m over r squared dr. And that's an integral that actually is not so hard to do. You probably know how to do it. First of all, let's bring the constants out. And then it's just the integral of r to the minus 2 dr. So that is going to, the integral there is going to be minus 1 over r. And there's another minus sign that we got to keep track of, with the limits of integration being the initial radial distance and the final radial distance. So this, when you plug in, what do you get at the end? You get equal to minus GMEM times 1 over RF minus 1 over RI. And I am going to get rid of my minus sign just by rearranging. So we can write this as G times ME little m times 1 over Ri minus 1 over Rf. And that's the way I calculate changes in gravitational potential energy using Newton's law. And just to check to make sure that we got the signs right, if we start close to the Earth and we go far away so that Ri is smaller than Rf, this is going to end up being a positive quantity. If Ri is less than Rf, then this term is bigger than this term, so we get a positive number, and that makes sense because we'd like it. It certainly has to be true that as you raise things and take them farther and farther away from Earth, the gravitational energy, potential energy should be increasing. Okay, so this is our important general result for, it's unique, not so general, it's unique to the Earth, but it gives us a way of calculating changes in gravitational potential energy, assuming we take objects that are outside the Earth's surface. It doesn't quite work if we go inside the Earth, but outside the Earth, this formula is completely general and correct. So I'd like to try to connect this formula, this generally correct formula, with our old way of looking at things where we were focused on elevations above the Earth's surface and see how the two connect, and also gain some insights as to when we can use the approximate form, when it's okay to use the approximate form, and when we need to use this more exact form. So I'm going to imagine a situation where the objects start at some initial, this mass, little m, starts at an elevation h sub I above the Earth's surface, and then moves to some final elevation h sub f. And the Earth is a sphere of radius r sub e. So the distance to the center of the Earth of each of these objects, it starts with an initial value to the distance of the center of the Earth of the radius of the Earth plus h sub I, and then it moves to a final position in which the distance to the center of the Earth is the radius of the Earth plus h sub f. So then I can write the change in the gravitational potential energy as I move from this initial to the final position as big G times the mass of the Earth times little m times 1 over, and I'm going to write r sub I as the radius of the Earth plus h sub I, minus 1 over r sub e plus h sub f. And now I'm just going to choose to rewrite this. I'm going to bring out a factor of r sub e in the denominator here, and I do that. That's legal, provided I write the denominators here as 1 plus h sub I over r sub e minus 1 over 1 plus h sub f over r sub e. That is certainly a legal thing to do. And now I'm going to make an important approximation. I want to consider, we're sort of looking to see when it's okay to use the approximate form, the mg delta h form. And our intuition is that that's going to work when, as long as we don't go too far from the Earth's surface. It's too far. What determines too far? Well, we want to compare the elevations that we're dealing with to the radius of the Earth, it turns out. So here's why I say that. Let's proceed in the following way. Let's assume that h sub I, both h sub I and h sub f, are small compared to the radius of the Earth. And that is Miles barking in the background. So I'm going to go calm him down. Okay, we're back. That was a UPS delivery, and Miles gets very excited with the UPS deliveries. Anyway, so we're going to consider cases. Suppose these elevations, both the initial one and the final one, are both small compared to the radius of the Earth. Well, then in the denominator here, these fractions, h sub I over r sub b and h sub f over r sub b, are both going to be small compared to 1. Now, why is that important? Well, here I want to take advantage of something which I've mentioned previously, but want to emphasize here. It's something known as the binomial approximation, which is a fancy name for the following fact. If you have an expression of the form 1 plus x raised to some power n, then the binomial approximation says that it is a good approximation to write such a quantity as 1 plus n times x. And the approximation is good, it applies well, provided that the absolute value of this quantity x is small compared to 1. Okay, so that's the binomial approximation. Well, with that in mind, I am going to write my expression for the change in the potential energy due to gravity as GMEM over RE times 1 plus HI over RE raised to the minus 1 power minus 1 plus HF over RE raised to the minus 1 power. All I've done is taken advantage of the fact that I can write 1 over something as that something raised to the minus 1 power. And why did I do that? Well, I was motivated by the fact that I notice if I write it this way, I can, this is really in the form of something where we can apply the binomial approximation, because I have something of the form of 1 plus some quantity whose absolute value is small compared to 1, because if hi is small compared to re, then this fraction here is going to be small compared to 1, and the same thing over here. So I've got the requirement of applying the binomial approximation is valid, and I can rewrite these. As long as I'm willing to put wiggly lines in here saying it's an approximation, I can rewrite the following line as follows. So I have delta U due to gravity. The change in gravitational potential energy is approximately, because I'm making use of this binomial approximation, big G, mass of the Earth, times little m over RE times, and now if I look at the binomial approximation, the thing that's playing the role of n is this minus 1 here. So I can rewrite this as 1 minus whatever x is. Okay, so if I do that, this becomes 1 minus h sub I over r sub e. And then I have a minus sign here, and then minus 1 minus h sub f over r sub e. Close parentheses. Okay. Well, if you look at what happens now, you'll see that the ones cancel. This one and this one subtract to 0. And what am I left with? I'm left with the change in gravitational potential energy is approximately G times the mass of the Earth times little m times, and now I have an HF over R sub E minus HI over R sub E. Okay. And I can rewrite this finally as, I'm going to just rearrange M times G times the mass of the Earth over the radius of the Earth squared times H sub F minus H sub I, like so. So that's the change in the gravitational potential energy. Now, is this looking familiar? It's remember, we're assuming we've made the approximation. When it's valid is going to be when the elevations are small compared to the radius of the Earth. And if that's true, the change in gravitational potential energy is m times this quantity here times the change in elevation. This we recognize is delta H. Okay, so anybody want to take a guess as to what the numerical value of this quantity is? Let's figure it out on the next slide. Okay, let's plug in the numbers. What is this quantity here? Plugging in the numbers. G is, so we're going to write down what is G times the mass of the Earth divided by the radius of the Earth squared. So G, we now know, Newton didn't know this, but we now know it, is 6.67 times 10 to the minus 11, and the units are newtons meters squared per kilogram squared, times the mass of the Earth, which is about 6 times 10 to the 24th kilograms, divided by the radius of the Earth squared. And the radius of the Earth is 6.4 times 10 to the 6th meters. Newton sort of knew that number. He just didn't know the value of the mass of the Earth or big G. Okay, so if we plug in these numbers to our calculator, we've got 6.67 times 6 over 6.4 squared. Those are all the non-exponents. And then in the numerator, I've got 24 minus 11 is 13, divided by 6 squared is 12, so that's a times 10 to the first. And you can sort of see that these things out in front here are going to be roughly equal to 1, right? I've got two factors of about 6 divided by about two factors of about 6. Any guesses as to the number we're going to get here and what the units are going to be? It's going to be equal to, of course, 9.8 meters per second squared. Right, that's the numerical value, and what that means is that our approximation here is provided we're at elevations close to the Earth's surface, it's a perfectly good approximation to say that the change in gravitational potential energy is just mg times delta H. So what we've shown is we've derived a rather exact form for how to calculate changes in potential energy due to Earth's gravity, which is necessary to use when we are at elevations which begin to become comparable to the radius of the Earth. But as long as the elevations that we're dealing with are small compared to the radius of the Earth, this approximate familiar form is a pretty good approximation. So the larger issue here is, how exact forms can often be approximated. The binomial approximation, which we made use of in this instance, shows up all the time in different calculations, and we'll in fact encounter it a few other times this term. So anyway, that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.